Signals and Systems, DT Fourier Transforms, Part 2, Properties, Series on Signals and Systems, Lecture number 5.12, Discrete Time Fourier Transforms, DTFTs. In short, they are useful to convert a non-periodic time domain sequence into frequency domain. In several properties, they are very much similar to CTFTs, that is, continuous time Fourier transforms. In the present session, the focus is on properties, important properties of DTFTs. Now, with this small introductory remarks, we move to the core session. We start the session by recollecting the definition of DTFT of a sequence. DTFT of a sequence X of n. It is usually indicated by X of omega. Omega stands for angular frequency. X of omega by definition is a summation sigma n minus infinity to plus infinity x of n e power minus j omega n. Notice this can be considered as a forward transform or transform which converts time domain signal into frequency domain or a sequence into frequency domain. Here notice x of n is in discrete time domain, whereas x of omega, it is in continuous frequency domain. Inverse transform gives x of n from x of omega. X of n is equal to 1 by 2 pi integral 2 pi x of omega e power j omega n d omega. Notice n is similar to t. This omega is similar to omega angular frequency 2 pi f. After having the defining relations in our minds, let us consider the properties, important properties. Linearity property. The transform obeys linearity. Mathematically, it can be stated as DTFT of A x of n plus B y of n is equal to A x of omega plus B y of omega. Time reversal. Transform of x of minus n is equal to x of minus omega. Time shifting. Transform of x of n minus n naught is equal to e power minus j omega n naught x of omega. Frequency shifting property. Transform of x of n e power j omega naught n is x of omega minus omega naught. Time expansion. Xm of n. Its transform is x of m omega. Modulation. Transform of the product x of n with the cos omega naught n is half x of omega plus omega naught plus x of omega minus omega naught. Conjugation. Transform of x of n conjugate is equal to x of minus omega conjugate. Frequency differentiation property. Transform of minus jn x of n is equal to first differential of x of omega. First difference. Transform of x of n minus x of n minus 1. It is equal to 1 minus e power minus j omega multiplied by x of omega, accumulation property, transform of summation x of k, k ranging minus infinity to n. It is pi x of 0 delta of omega plus 1 by 1 minus e power minus j omega x of omega. Convolution property. Transform of convolution between x1 of n and x2 of n. It is equal to x1 of omega into x2 of omega. Multiplication property. Transform of the product x1 of n and x2 of n is equal to 1 by 2 pi x1 of omega circular convolution with x2 of omega. So far, a listing of important properties of DTFTs. Listing is given. Now we go a little bit deep into each one of these properties to see, to find the validity of these properties. We begin this exploration with the linearity property. In simplest possible terms, linearity is superposition principle. In terms of mathematics, linearity property can be stated as transform DTFT of A x of n plus B y of n. It is equal to A x of omega plus B y of omega. Notice x of omega is transform of x of n. B of omega is transform of B of y of n. In time domain, x of n is weighed by A. Y of n is weighed by B. In frequency domain, x of omega is weighed by same A in y of omega. Y of omega in frequency domain, it is weighed by same B. So weighing is the same. The linearity property states that the DTFT of a weighted sum of two signals. This is weighted sum. Plus is there. Weighted sum of two signals is equal to same weighted sum of A and B. They are there in the frequency domain too. Same weighted sum of individual DTFTs. Proof is trivial. Now we consider time reversal property. According to this property, DTFT of x of minus n is equal to x of minus omega. How to prove this relation? Apply Fourier transform definition, both sides. Fourier transform, here DTFT applied to x of minus n. This sequence is sigma n minus infinity to plus infinity x of minus n e power minus j omega n. Now it can be expressed as sigma n minus infinity to plus infinity x of n e power minus j minus omega n, which is of course x of minus omega. So DTFT of x of minus n is x of minus omega. Time reversal property. Time shifting, another property, is considered right now. DTFT of x of n minus n naught is equal to e power minus j omega n naught x of omega. To understand this property a little more deeply, consider DTFT of x of n. It is equal to sigma n equal to minus infinity to plus infinity x of n e power minus j omega n. Transform of x of n minus n naught is summation n from minus infinity to plus infinity x of n minus n naught e power minus j omega n. Let n minus n naught equal to k. Then DTFT of x of n minus n naught becomes equal to sigma k equal to minus infinity to plus infinity x of k e power minus j omega k plus n naught. Now e power minus j omega n naught has been brought out of the summation. The remaining part can be identified as x of omega. Therefore, transform of x of n minus n naught becomes e power minus j omega n naught multiplied by x of omega. Then we consider shifting property, frequency shifting property. DTFT of x of n e power j omega naught n is equal to x of omega minus omega naught. Notice in time shifting property, shift is in time domain. In frequency shifting property, shift is in frequency domain. In time shifting property, multiplication with exponential function is on frequency domain, whereas in frequency shifting property, multiplication with exponential function is in time domain. Certain similarity, parallelism is in these two properties. Now apply DTFT to product of two signals x of n multiplied by e power j omega naught n. According to the definition, it is sigma n equal to minus infinity to plus infinity x of n e power minus j omega n e power j omega naught n. This can be written as sigma n minus infinity to plus infinity x of n e power minus j omega minus omega naught. This can be identified as x of omega minus omega naught. Now time expansion property. Fourier transform, that is discrete time Fourier transform of xm of n is equal to x of m omega. The signal xm of n, notice it is defined as x of n by m. If n is multiple of m and is 0, if n is not multiple of m. Time expansion. This is the definition of x m of n. It has m minus 1 zeros inserted between successive values of the original signal. So this last point statement gives you a great deal of understanding regarding x m of n. If m minus 1 zeros are inserted, the signal gets expanded. That is xm of n. Now its the transform is becomes x of m omega. Let n equal to km, then Fourier transform of xm of n e power j omega naught n. Its DTFT is sigma k equal to minus infinity to plus infinity x of km by m multiplied by e power minus j omega km. It is equal to sigma k equal to minus infinity to plus infinity x of k e power minus j omega km. Now this can be identified as x of m omega. Hence transform of x m of n is equal to x of m omega. Now we consider another property, conjugation. Transform of x of n conjugate is equal to x of minus omega conjugate. How this relation has come into being? To see that, apply transform to x of n conjugate. By definition, it is equal to summation n ranging from minus infinity to infinity x of n conjugate multiplied by e power minus j omega n. Now this summation can be expressed as sigma n minus infinity to plus infinity x of n e power j omega n conjugate. Of course, it becomes x minus omega conjugate. Another property we consider right now, frequency differentiation. Transform of product n x of n. It is equal to j first differential of capital X with respect to omega. Notice differentiation is in frequency domain, whereas multiplication with n is in time domain. To understand this property a little more deeply, apply the definition of transform to the product n x of n. It is equal to sigma n equal to minus infinity to plus infinity n x of n e power minus j omega n. It is equal to j sigma n minus infinity to plus infinity dx of n by d omega e power minus j omega n. D by d omega can be brought out. It gives us j d by d omega sigma n equal to minus infinity to infinity x of n e power minus j omega n. Now this can be identified as j dx by d omega. Another property, first difference property. The transform of the difference x of n minus 1 or transform of x of n minus x of n minus 1. It is equal to 1 minus e power minus j omega multiplied by x of omega. To know how this property has come into being, you consider the transform of x of n minus x of n minus 1. Using linearity property, it can be shown this is equal to transform of x of n minus transform of x of n minus 1. Transform of x of n is x of omega. Transform of x of n minus 1 is e power minus j omega x of omega. Therefore, transform of the difference x of n and x of n minus 1 becomes equal to 1 minus e power minus j omega multiplied by x of omega. Another property, convolution property. Transform of convolution between two sequences x1 and x2. It is equal to product of their transforms x1 of omega and x2 of omega. The convolution in time domain is multiplication in frequency according to convolution. Okay, to see a little bit more deep into this property, consider DTFT of convolution of two signals x1 and x2. By definition, it is equal to sigma n minus infinity to infinity, sigma k minus infinity to infinity, x1 of k multiplied by x2 of n minus k e power minus j omega n. This expression can be reformatted, and in that reformatted expression we can see the product x1 of omega and x2 of omega. Now we consider multiplication property. Multiplication in time domain. Transform of product x1 and x2. It is equal to 1 by 2 pi circular convolution between x1 omega, x2 omega, or x1 of omega, x2 of omega. To understand a little bit deep about this property, consider transform of the product x1 and x2. It is equal to sigma n equal to minus infinity to infinity x1 of n 1 by 2 pi integration over a range of 2 pi x2 of omega e power j omega n d omega e power minus j omega. Here x2 of n is expressed in terms of x2 of omega, inverse transform. Now this can be manipulated. a little bit and can be seen as 1 by 2 pi x1 of omega circular convolution with x2 of omega. Now we come to the end of the present session. Before closing down, let us recollect the important aspects that are touched upon in the present session. The beginning of the session is with the recollection of the definition of discrete time Fourier transform, and then a listing of properties of the transforms. It is given, and then an explanation, a description regarding the properties of DTFT are given. Hope this session is useful to you. We meet again in another session with a new topic soon.